Good morning to you. I'd like to go through like some of all I did with this is I just took a look and just scored this, statistically speaking, how many correct answers did I have. So I figured I could share that with you. Again, this was not for points, that type of application where I asked you to remove all items from your desk and identify the alpha groups. So I had 29 students turn in papers. So 16 out of 29 identified isopropyl correctly on the spot without any help at this early stage in anticipation of a test on November 10th. So that's 55%. And we'll go through the rest. And this was N-propyl. 58% of students identified it correctly. Here we had isobutyl. That was 45% of students identified that correctly. I believe just the way that the N-butyl was drawn was a point of confusion for students. Maybe if the N-butyl was drawn in the way you were accustomed to, then that would have led to higher marks. Nevertheless, it is N-butyl because you have four carbons in all, and on each of those vertexes, there's no further branching. So it is an N-butyl. So hopefully you maybe understand that a little bit better, that proof. Following N-butyl, we had ethyl. So 83% of students identified ethyl correctly. Following ethyl, we had methyl. Again, 83% of students identified methyl correctly. After methyl, this was S-butyl. So more students identified S-butyl than they identified N-butyl, again, because I think just the N-butyl was drawn in a confusing way. That was 38%. And finally, 52% of students identified Chi-butyl correctly. And last time we had discussed cycloalkane IUPAC nomenclature. So please turn in those homeworks at the end. And as advance notice was provided, we will be in keeping with last year, moving into chapter 5 and revisiting chapter 4, which has more memorization information and compartmentalized information in December. I do have certain slides. If you take a look at the chapter 5 items, these PowerPoints with chemistry drawing figures that I made don't always turn out well based on my previous experience. So I provided those, and we'll be starting at those handouts for today. And I have a homework, and I may provide that to you. The homework will probably be asked for Wednesday. So you don't have any homework due on Monday, because you did have 2 homework assignments due today. Updating attendance. Okay, so that was for openers. Anything to ask? No, okay. We'll be working off of this handout here, the upper one, 5-3 chiral atoms, molecules, sigmas. Be doing that now. Here is a worksheet for everybody. Hopefully you have a pencil handy. Welcome to chapter 5. We will re-enter chapter 4 with the rest of its memorization content in December. Leaving chapter 4 for now, entering chapter 5. But this one is so please bring this back on Monday. Let this new one. So we're having a collection of molecules on this page with this blue dotted line. Did you catch that? Made a color copy for you, a blue dotted line. This line is supposed to possibly be a sigma. It's pronounced sigma. That's the symbol that they chose. I know it's the same as the sigma bond, but it's sigma. And this is called formally an internal mirror plane of symmetry. A sigma is an internal mirror plane of symmetry. The sigma is trying to be an equal sign. It's attempting to be an equal sign. Is it such that the left side of the molecule given L resembles exactly, all the bonds resemble the right side of the molecule? Is it that the case? Is the left side of the molecule exactly resembling the right side of the molecule? Try it out. A sigma is a plane. It's a plane. It's a plane. It's a flat sheet of paper. It's a plane. This is a sigma here. This is a sigma. It's a plane. I could try this. Is the left side of the molecule identical to the right side of the molecule? Is it here? This is a sigma. A sigma is a plane. It's a two-dimensional paper, which you're trying to see is the molecule the same on the left side and the right side. So we'll treat these one by one and see if you believe that this is a sigma or not. So is this a sigma? Attempting a sigma here for A. We're looking at A. Is A a sigma? Is the left correct? Thank you, Hayden. It is not. So you would put no sigma here. Is the left half of the molecule identical to the right half of the molecule? No, because you're kind of missing this bond here, aren't you? That's missing. So how could it be at 100% the same? Do you follow? Okay. So far, so good. I have your stamp of approval to proceed. All right, thank you. Let's go try the next one. Is this a sigma? Is the left half molecule identical, 100% identical to the right? Correct, Molly, it is not. So I made, again, put no sigma. How could you say that a wedge is the same as a hash? By definition, it's not. I put the definitions on the board. A wedge is to the front, not a sigma. I even put this eraser holder right next to the wedge, right? The wedge is supposed to be sticking out at you. And isn't this eraser holder sticking out of the board, right? So we're in a chapter about stereochemistry. Stereo, remember the Greek and Latin handout refers to three-dimensional. back in the 50s, they used to call 3D movies stereo movies, actually. And so in terms of bonds, you know, there's an in-plane bond, a wedge bond, which is closer, this eraser holder, and a hash bond, which is further away or back and behind. The molecule I think we're looking at is yep, this is it. I'm attempting that blue sigma. You remember the blue dotted line? This is it. In real life, this is it. Piece of paper. And where red is oxygen, white is hydrogen. Certainly not the same. That's not the same. The left half is not 100% equal to the right half. For the next one, it is. That's a sigma. Cut that like that. In other words, if I hid this from you, and I just gave you the left half of the molecule, you will be able to, from the sigma, derive the right half of the molecule. Yeah, because you already know the left half, the right half should look just like it. So C is a sigma. And there's plenty more examples to go. Just listening for any questions you would have. It's your first example of a sigma, and it's a very nice example. Yes, this is a sigma. You can count the carbons: 1, register 2, 3, and 4 carbons from the sigma, and that mirrors. Sometimes sigmas are called mirrors. The left half of the molecule mirrors the right half. And you got a hash, you got a hash, you got an oxygen, you got an oxygen, exactly the same, 100% identical. That's a sigma. That is a true blue sigma. Any questions? So far, so good. May I proceed? Okay, let's see what's next then. Is this a sigma? Yes or no? Correct. Thank you, Ricky. It is not. How could you say that oxygen with 8 protons is the same as N with 7 protons? So that's too bad. But everything has to be exactly the same. So it's not a sigma. So we want to put in that. So I hope the first line went well for you. Okay, good. You'll be getting. You can pick it up today, or else you can just let it go. I'll give it to you on Monday, but I do have a homework set for you about this. So we'll go down to the next row. We'll put this on the marker board. See if I can frame this. I'm just taping this out of consideration. This is an important lecture today for students who are missing, so I just barely remembered in time to record it for what it's worth. So right now, it doesn't look like it has a sigma. Doesn't look it. So this is a very good tool I'm going to share with you now. You're familiar with main chains with zigzag. You can draw main chains like this, and this is really helpful for chapter 5. Here goes. More symmetrical, right? Remember, single bonds are flexible. Now let's try. This is containing 6 carbon atoms. So far, so good. think I put too many on there. Did I? Did I miscopy that? I think I did. That's 7. Yeah, okay, good. So I can write the main chain almost like this, 7. You put carbon 3 having a chlorine and carbon 4 having a chlorine. And attempt a sigma. Still doesn't look too good, right? Yep, so the answer here is no sigma. We tried it with the most symmetrical way. You could have tried it like this as well. 3, 4, 2, 1, 2, 1, 5, 6, 7. So that 7th carbon dismisses the sigma. That's also, so is that a sigma? No, that is not a sigma. So this is going to enter, and the final answer is no sigma. It can be redrawn. I could have just done this on the computer. Like this. Just taking our time with these examples, covering them thoroughly. Number the main chain, if you like. 7. Same molecule, right? Chlorine and carbon 3, chlorine and carbon 4. Do you buy it's the same molecule? Okay. We're going to go ahead then. May I go ahead? Okay, thank you. Let's see what's next then. Forgive me if I'm going too slow. So this is the classic strategy. If you are trying to see whether or not a molecule has a sigma or an internal mirror plane symmetry where the left half of the molecule looks the exact same as the right half of the molecule, what to do, what to do, what to do. Try to input a sigma so that there is one group to the left and one group to the right of the sigma. One chlorine to the left of the sigma, one chlorine or whatever. You have a hydroxyl or something. To the left, one group to the right. Try that. That's the only way you can get a sigma, because you cannot have a sigma, meaning same, if you have 2 chlorines to the left and none to the right. It's not going to work. So one group to the left, one group to the right. That's the only way we can hope to have a sigma. If you have an even Steven, 1 chlorine to the left, 1 chlorine to the right. And then I can count here. If I arbitrarily make this carbon 3, it's going to be carbon 4, go backtrack to 1. The carbon count looks right. You can verify that. 2, 1. And this is a nice example of a sigma where the molecule has 2 of a, if you remember the term, hetero group, something other than carbon or hydrogen. A nice example of a sigma provided to you. I think E and G are the same molecule, so we'll go on to H. Yep. Going to H now. This is what to do in case you only have one of something. There's only one chlorine atom. So I made a molecule. Pretend this chlorine is like a green apple. Have you ever taken a knife and cut an apple in half? Atoms are spheres, right? Atoms are spheres. And when you have one of something, try to bisect it, almost like you're cutting an apple or an orange in half. Here's a sigma. I cut it in half. I could do that with a pair of scissors if I wanted to and ruin the plastic piece, but I won't do that. So when you have one of something, try to bisect that atom. It's atoms are spheres. So when you have one of something, akin to cut the apple in half. That's the only way you can hope to have a sigma. If there's one of something, cut the apple, try to cut the apple, pretend the atom is an apple, cut the apple. There's a red apple. Cut the apple in half. Or the atom. Bisect the atom letter itself. Atoms are spheres. Yes, this does have a sigma. A very nice example. Yes.
What if it's like an alcohol or like this NH2? Is it the same thing?
Yes, it's the same thing. It's a very good question. Thank you, John. Very good question. What happens if this was OH instead of OH is O atom and H atom? Treat it the same. Treat it the same. We'll do one of those examples. I made a model over here of the OH. And I think we're going to scroll down now. I'm going to go down to the next slide. Do you have any questions? I'm going to keep going now, okay? All right, here goes. Like this real life model example. I can bisect the ring. See, that's a sigma. And I can bisect the red atom and the white atom all at once. This does have a sigma. Yes. When you have one of something, cut the apple in half. Yes, there's a sigma, yes. Gonna keep going. So far, so good. I hope you're doing well with this. This is the first tool that goes in the toolbox for chapter 5. The toolbox is empty now for chapter 5. We put the first tool in it. How about this one? Does this have a sigma? Yep. Thank you, Molly. Correct, you are. This does have a sigma. J is yes, if that's a J. Yep. Yes. A symmetrical molecule, in other words. It does have a sigma. How about K? Is this a sigma? Correct again, Molly. It is not. If it was, then you needed to have a double bond here. All it takes is one thing to throw it off. It's not 100, not 95%, 100% exactly the same. It's 95% the same, but it needed that double bond to clinch 100% same. How could you say that a double bond is the same as a single bond? Not a sigma. And how about this one? Is that a sigma? Correct, but Ms. Maley, it is not. How could you say that a wedge is the same as a hash? Oh, it's so close, but it's not a sigma. Nope, not a sigma. just updating attendance for us. Going to leave this page now. Questions? As I said, you'll probably get a homework on this on Monday, due on Wednesday. So that means you can ask questions on Tuesday. That worked well. The next thing we'll be doing is identifying chiral carbon atoms. Chiral, handed, left-handed or right-handed. So we just identify whether or not these molecules contain segments. Now we'll be looking at whether or not molecules have chiral carbon atoms. So that's the next worksheet. I'm going to give you a primer before that. Here are some work examples and a strategy about how to show and complete these types of problems. I saved you some writing and copying from the marker board. This is the strategy sheet or the introduction sheet for identifying chiral carbon atoms. How many bonds does carbon make? You know? Four, correct. Moving it along. So chiral means if the atom is to be chiral, that carbon will have 1, 2, 3, 4 different groups on it. Chiral. I look at the word dynamic. I'll be up. We're doing the chirality discussion in a moment. I want to take stock of who I may have missed with the handouts. So, did anyone not receive the packet? The brand new packet? I never received it. Anyone else that I have missed? Raise your hand, Rashida, the next time. I'll walk back. Chiral, the word chiral. That's a spelling. I'm writing chiral on the board. I use the word to help me define it. Look at the word chiral, guys. It starts with a C, which is a different alphabet letter than an H, which is a different alphabet letter than an I, which is a different alphabet letter than the R. So this says a hint to the wise is sufficient. A chiral carbon atom has 1, 2, 3, 4 different groups on it. That's what makes a chiral atom a chiral atom. 1, 2, 3, 4 different groups on it. Yep. So we're heading this handout. I made this today. A chiral carbon vertex. Yeah, I said vertex on purpose. You will never have a chiral atom, which is an endpoint. Okay, this is the second thing that goes in the toolbox for chapter 5, identifying whether or not a vertex is chiral. So a chiral, this is the definition. A chiral carbon vertex is a carbon vertex bond to 4 different unique groups. Maybe it's one chlorine is bonded to an OH, and it's bonded to an N propyl, and it's bonded to an H, and it's bonded to a methyl. 1, 2, 3, 4 different groups. Maybe another chiral carbon atom is bonded. This vertex is bonded to a phosphorus, and that vertex is bonded to a hydrogen. That vertex is also bonded to an ethyl, and that vertex is bonded to a methyl. 1, 2, 3, 4 different groups. We label them, and this isn't just something that I woke up with. Oh, let's just do it with asterisks. No, this is the universal label for chiral carbon atoms is an asterisk. So it's not something that I just said, well, let's just do this on this campus. We'll label them with asterisks. So no, in the textbooks, they are labeled with asterisks. So guys, I can cut your work short. You're going to be given molecules. as you see on this page, zooming out, and on your homework too, these are the molecules, and we'll be labeling chiral carbon atoms with asterisks. The asterisk on the keyboard is if you hit Shift and the number 8, you get an asterisk on the screen. So you're given a molecule and you're asked to label asterisk carbon atoms, which are chiral. 1, 2, 3, 4 different groups on them. Any questions? So when we do these, and I have some on the marker board already, if the camera can make its way over there. When we do these, we're going to ignore certain carbons from consideration. Ignore unbranched carbon vertexes. If it's not branched, it has no possibility to be a chiral 1, 2, 3, 4 different groups carbon atom. Do you follow?
So it's just like a line of carbon. It doesn't have any chiral.
Correct, like heptane, would not have any chiral asterisk carbon atoms in it, correct?
Only when it branches off with a heteroatom.
Yeah, heteroatom, or even an alkyl branch, providing it's in the correct location, as you'll see with plentiful examples. Also, we will ignore double bonded carbon vertexes because it's bonded to the same thing twice, right? If you're supposed to have something which is chiral, and if you're bonding to the same thing twice, how can you have 4 different things? Ignore triple bonded carbon vertex. This is making our work short. We only have to investigate single bonded carbon atoms which have branches. We'll have to run a check. Could be, maybe not. These are going to be asterisk carbon atoms which are chiral. Insider's tip there. What to ignore, what to check. Here are some worked examples. Take a look at this molecule as received. It's in the blue box. Oh no, you know something? I'm not sharing this. Oh, that's too bad. Oh yeah. Take a look at this molecule. It's in the blue box. Okay. All right. Am I concerned about this carbon here? Dots. Not at all. Double bonded. Skip along, please. Move along. Am I concerned about this carbon being chiral? Nope. Double bonded. You can move along. Am I concerned about this carbon being chiral? Nope. Not branched. Please move along. Nothing to see here. Am I concerned about this carbon being chiral? Possibly. It's branched. It's singly bonded. I'll have to run a check on that. I'm not concerned about this. It's not a branch. I'm not concerned about that. You will never have an endpoint. There are 3 hydrogens here, right? You know this from line angle formula. That's why we spent so long on line angle formula chapter 1. That way you'll be up to speed when we do stuff which depends upon line angle. There are 3 hydrogens here. So if you're supposed to have 1, 2, 3, 4 different groups, and we have 3 hydrogens, how are you going to get 4 different groups? You can't. And so we're going to run a check on this carbon here, which has the question mark. So we reduced all this down to investigating 1 carbon, which is singly bonded and branched. So far, so good. What are the branches on this? I put a peg chip there now, kindly for you on your paper. Sending you some copy work from the marker board. What are the substituents? This peg chip has a chlorine. Are you with me? So far, so good. It also has a hydrogen, which is not shown, is it? Is the number of hydrogens is equal to 4 minus the number of bonds, right? So there's a hydrogen there. Line angle formula. How many hydrogens equal to 4 minus the number of bonds already present? There's a hydrogen there. Where's the ethyl group at? Look off the peg chip. That's your frame of reference. That's where you're standing now. Like I'm standing on this tile on the floor here, on this kind of square tile. I'm standing there. My frame of reference is the peg chip. Off of this peg chip, please watch how I circle this class. I'm bisecting the bonds. I'm circling at the bond midpoint. This is an ethyl, as you have learned it. 1 carbon, 2 carbon. That's ethyl. Are you with me there? Sound good to you? Thank you. Very good. And whatever this group is, the large group to the left, we don't have to name it. I couldn't name it. It'll take me a few minutes to cook up a name for that. A chlorine, and there was a hydrogen there. You betcha. That's 1, 2, 3, 4 different groups. This carbon atom is chiral. Are you with me? Okay, good. What your next homework about? You can take it today if you like. And once you have identified it as such, you finalize that and announce it to your audience with an asterisk. That's your final answer. The same molecule, but with one vertex carefully asterisk. And as I said, that's not something that I said, oh, this year, let's use asterisks on this campus in 2021. No, they've been using asterisks for years and years and years across all of chemistry. So this is the universal symbol for a chiral carbon. It's an asterisk. So I just want to let you know that this is not something that I've come up with. This is everywhere. They use asterisks. That's the symbol to this day. And after we come down to see this example number 2, then we'll try some more fresh examples at 8:37. So far, so good? Good. Take a look at this nice example here. My screen sharing, yes, I am. It's not branched, I'm not going to worry about it. It's not branched, I'm not going to worry about it. Not branched, I'm not going to worry about it. Ding, ding, ding. Watch this one. We gotta wonder about that one. With a Riddler question mark there. Could be, maybe not, but I gotta check it. Not branched, not going to worry about it. Ooh, branch. Gotta check that. Gotta run a check. Could be, maybe not. Unbranched, not going to worry about it. Unbranched, not going to worry about it. So far, so good. All right. So, are you still with me? Technical lecture today. Thank you for hanging with this. So, let's investigate this one. Well, I'm going to zoom in and let's decide upon this one. We're going to see that this carbon here, this asterisk is chiral, because on this green question mark, nice, you have a nice colored coffee, right? This green question mark, you have a methyl. And there was a hydrogen there. It's actually on a wedge because each carbon goes in plane, wedge, hash. Remember, you had not one, but 2 homeworks on how many hydrogens. You had plentiful homeworks in chapter 1. This is why. Hopefully you can determine there's 1 hydrogen there without too much fuss. And over here, this is an N-propyl. Please watch how carefully I circle it. And I would hope you would circle it on your paper copy the same way, the exact same way. Look how this is the correct way to circle it. When you circle it, you do not want to run over any vertexes, or else you're gonna mess it up. So look how the circle is at the bond midpoint. You'll have less mistakes that way. You'll tamp down on mistakes. And that's an N-propyl, which is different than a hydrogen, which is different than a methyl, when whatever this is. We don't have to name it. It's not in your job repertoire to give this an IUPAC name. You don't have to, but it's a big group. It's the group to the right. The group to the right. So there's 4. You can't say that the N-propyl is the same as this, can you? Not the same. They have a different number of carbons, right? So you can't say that. So you do have 4 different groups, and so this is going to be chiral. And off to the right, and we're ready to go on the examples in a moment. This is geminal, actually, if you remember that word geminal. Geminal, Gemini twins. This carbon here at the peg chip, don't you know it, is bonded to 2 ethyls. One just happens to be in happenstance on a hash. It's an ethyl though, right? 1 carbon, 2 carbon, count the carbon, prove it to yourself. This is an ethyl as well. 1 carbon, 2 carbon. There are 2 ethyls. So if you have a chiral carbon, then you have to have 4 different groups. Right away, the game's over. You need not proceed further. Game's over right now. Ethyl. Might as well stop. Save your time. you find identical groups, it can't be chiral. I just showed you the rest of it just to do a complete job. But if you find two ethyls or two N-propyls right away, why press on? You've already decided that it's not chiral. But maybe you found the fourth ethyl group last, so the way you did it. But, so your final answer will have a molecule and with one asterisk. So let's try some out then. Try some fresh molecules. Do you have any questions? So at the beginning of the period, we talked about sigmas, and now we're talking about whether or not you have any asterisk carbon chiral atoms. It's a very important lecture today. That's why I'm tape recording it for students who aren't here. As you see, some of the tape recording has become messed up because I have to share the screen, but it's better than nothing. And I'll share for that. Okay. Look at molecule number 1. Okay. Well, we're determining, let me ask you this first. Does this molecule have a sigma? Correct, Hayden, it does not. Let me ask you about sigmas. Remember sigmas? Is this a sigma? Can I show you at that? Almost like at a used car lot. Is this a sigma? Nope. Not a sigma, correct? Are you with me? Okay, that's not a sigma. Is this a sigma? Good. It's not a sigma. You would need a chlorine off to here, don't you? You need a chlorine somewhere over there to balance the other chlorine. No sigma here. No sigma. So you know about sigmas. Now let's check chirality. Are you going to worry about this carbon? Nope. Not branched. It's not even a vertex. 3 hydrogens there. You're looking for a carbon atom which has 1, 2, 3, 4 different groups. This one has 1, 2, 3 hydrogens. They're not. They're the same. Replicates hydrogens. I'm not going to worry about this one, right? Not branched. Skip right along. This one. Let's check this one. This could be it. This could be, maybe not. We'll find out. What are the substituents on that question mark carbon? What is this carbon question mark bonded to? Let's make a list like you saw on that worksheet I gave you earlier. Anyone want to say what this carbon is bonded to? I'll put a picture up there. Thinking, you go ahead. Floor is yours.
It's all of them or just one of them?
All of them, please.
Okay. Carbons connected to fluorine, hydrogen, an ethyl group, and a methyl group.
Correct. Thank you. You said that this peg chip here, your classmate said this bond, you have a chlorine, right? You see that? Off of this blue chip carbon atom, which is branched. At the same time, you have a hydrogen. And to the left of the peg chip, we see a 2-carbon ethyl group. I just circled it. You can use the abbreviation, that's why I taught it to you. To the right of the peg chip, you see a 1-carbon, endpoints of carbon, methyl group. That's the methyl. We have 4 different groups on it. This is chiral. Chiral. And we would mark this with an asterisk. Your final answer should have an asterisk and that announces to your audience that, yep, this is chiral. You know something? This is why pharmaceutical drugs in this country cost so much, because it's very difficult to synthesize back in the lab chiral carbon atoms. That's why we're having such a problem with how high drug costs are. I'll tell you about that more as Chapter 5 draws to a close. But there are repercussions, serious repercussions. If you were to go to make this in laboratory, this is a hard job to make that. Very difficult to make that pure. Because why do we have side effects from drugs? You know, you take a drug and your physician may say, oh, be on the lookout for the side effects. Side effects from drugs are due to impurities in the drugs. So if you can't make that 100% pure, you're going to have side effects, and it's going to be difficult to make that pure because it's a chiral carbon, as to be discussed in the future. But to let you know, there are serious repercussions for if you have a chiral carbon. Does this molecule have a sigma? Number 2. Oh, I forgot I have a highlighter. Isn't that nice? If it works. Once that gets started there. I give up. If you have one of something, pretend it's a green apple or whatever, an orange or whatever. This is a sigma, guys. That's a nice sigma. Isn't that a nice sigma? If you have one of something, cut the apple or atom in half. Get one of them. That's a sigma. Register a sigma. Have any questions? May I proceed? Okay. Erase this. And now we'll look at its possible chirality. We're thinking this one here. Huh? Could be. Could be a little bit of a delay here. Is this peg-shaped carbon a chiral carbon? Correct, Hayden, it is not. Thank you, Molly, it is not. What would you say, Hayden? What is the explanation? Wonderful answer, thank you. So 2 ethyl groups. Definitely on a delay. 2 ethyl groups. Ethyl, repeat. Game's over already, guys. Game's over. You need not, if you want to generate the rest of the list, it's a hydrogen at that peg tip and a chlorine. Ready to move on. Okay, may I? All right, let's see the next one then. The molecules change, but the rules stay the same. Are you concerned about this one? Nope, double bonded, bonded to the same thing twice. So how could it have 1, 2, 3, 4 different groups on it? Nope. This molecule has no chiral carbons. You would just leave it blank. Of course, I know you know you guys are smart and stuff, so I know you know there's no sigma there. Looks like we got 2 to check here, huh? I would check this one, and I would check this one. One of these question marks will be a chiral carbon atom. Which one is it? The upper question mark or the lower question? Yes, the upper one, correct. Because the lower one, you have 2 methyls. So this is it. Thank you very much. Good answer in the nick of time. Can you list our groups, Jahim, to close our class?
Hydrogen, chlorine, and isopropyl.
Correct. Thank you. It doesn't matter the order in which you list them. This carbon with the asterisk is the chlorine, and you identified isopropyl very well. So it's nice those alkyl groups are fresh in our minds after multiple homeworks on that. If you wanted to try your hand at the upcoming homework, I'll put it on a chair. If there's a chair at the front of the room. And thank you very much for coming today. Today was a very important lecture. I didn't want to say that up front. But if you have homework for me, you can turn it in up here at the table somewhere. Have a good day. Good stuff. Yeah.